So let's kind of summarize the stellar properties we've looked at so far. We've looked at distance. We can use parallax for nearby stars and the standard candle method for measuring the distance to further stars. Temperature, we can either use Wayne's law or spectral class to determine its temperature. Luminosity, we can measure the star's apparent brightness and distance and then calculate it using the inverse square law. Or we can talk about luminosity class just by the spectrum. We haven't talked about that, but it's another way of determining luminosity. And we can also measure its composition, the spectral lines observed in a star. We can measure its radius using the Stefan-Boltzmann law to measure luminosity and temperature, solve for radius. We can use an interferometer, which gives angular size of the star from distance and angular size for nearby stars. Or we can use an eclipsing binary light curve to determine radius. Mass, we use Kepler's third law applied to binary stars. And radial velocity, looking at the Doppler shift of the spectrum lines. So all this information is determined just by looking at the light of the stars. Now, we've done this. We've measured all these properties of all these different stars. Now we're trying to get a big picture. How do we put it all together? The next step, of course, now is to understand why stars have properties in the combinations observed. And this step in our understanding comes from the HR diagram, developed by two different scientists, Injar Hertzsprung and Henry Norris Russell, in 1912. The HR diagram is a plot of stellar temperature versus luminosity. Now, when we do this, most of the stars on the HR diagram lie along a smooth diagonal running from the hot luminous stars in the upper left of the diagram to the cool dim ones in the lower right part of the diagram. By tradition, bright stars are placed at the top of the HR diagram and dim ones at the bottom, while high temperature stars are on the left and cool ones on the right. Now, when you normally see a graph, it usually starts out with low numbers to high numbers. So it's backwards on the temperature here. And that's just by tradition, and we're pretty well stuck with it at this point. So, in the HR diagram, stars over here are hotter than the ones over here. And the ones down here are dim, and the ones up here are bright. The diagonal running group of stars on the HR diagram is called the main sequence. Generally, in any group of stars you look at, 90% of the group of stars will be on the main sequence. However, a few stars will be cool but very luminous, the upper right of the HR diagram, while others will be dim and very hot, the lower left of the HR diagram. The Stefan-Boltzmann law is the key to understanding the HR diagram. For stars of a given temperature, the larger the radius, the larger the luminosity. Therefore, for a given temperature, as one moves up the HR diagram, a star's radius must become bigger. On the other hand, for a given luminosity, the larger the radius, the smaller the temperature. Therefore, for a given luminosity, as one moves right on the HR diagram, the star's radius must increase. The net effect is that the smallest stars are in the lower left corner and the largest stars are in the upper right. We can actually then plot the radius of stars on our HR diagram. The ones down here are about 1/100th of the size of our Sun. And as we get further and further here, we get ones that are 1,000 or more times the radius of our Sun. Those stars in the upper left are called red giants. They're red because they're low temperature, and that therefore they're going to be more red than white. Stars in the lower right then are white dwarfs. And so we have three stellar types: main sequence, red giants, and white dwarfs. Giants, dwarfs, and main sequence stars also differ in average density, not just diameter. Typical density of main sequence stars is about 1 gram per cubic centimeter, while for a giant it's 1/1,000,000th less. Now, when putting all these all together on the HI diagram, another relation was discovered: the mass-luminosity relation. Main sequence stars obey this, and it's approximately given by the luminosity is equal to the mass cubed, when luminosity and mass are measured in solar units. So consequently, stars at the top of the main sequence are more massive than the stars lower down. Now another method was discovered to measure the luminosity of the star, other than its apparent magnitude and inverse square law. It was noticed that some stars had very narrow absorption lines compared to other stars of the same temperature. It was also noticed that luminous stars had narrower lines than less luminous stars. So the width of the absorption line depends on density. Wide for high density, narrow for low density. So then if I look at the high and low density stars, even the same spectra, you see they're wider for high density than they are for low density. So luminous stars, and again in the upper right of the HR diagram, tend to be less dense, hence they had narrow absorption lines. So now the HR diagram can be broken into luminosity classes. 1, the bright supergiants, 1A and 1B, the supergiants, 2, the bright giants, 3, giants, 4, subgiants, and 5, the main sequence stars. So now the Sun is a G2-5 star. Right, to summarize these, most stars lie on the main sequence. Of these, the hottest stars are blue and more luminous, while the coolest are red and dim. A star's position on the sequence determines its mass, being more mass near the top of the sequence. And we have 3 classes of stars. We have the main sequence, we have the giants, and we have the dwarfs. Not all stars have a constant luminosity. Some change in brightness, and we call those variable stars. There are several varieties of stars that vary and are important distance indicators in astronomy. Especially important are the pulsing variable stars, stars with rhythmic swelling and shrinking radii. 2 different types are the Mira and the Cepheid variable, and they're classified by the shape and period of their light curves. The Mira stars, the period is sometimes over several hundred days, so in this case the period is 200 days for this star. The Cepheid variables are a short period variable star, and their period is 3 to 4 days. Now if we look at variable stars, they lie on something called the instability strip, the strip on the HR diagram. Notice stars like Polaris, our North Star, are variable stars. This concludes everything we're going to talk about in Chapter 10.